It's a pleasure to be part of this conference. This talk will be like this morning's other talk in that what it's focusing on is a line of literature that relaxes assumptions about what exactly people know about the situation that they're in. And I think over the last decade or so, particularly in the macroeconomics literature, there's been a revival in interest in the role of incomplete information about the current state of the economy in explaining outcomes. That's, of course, not entirely a new theme, but I think the most recent literature on it, at least much of it, has a different flavor than the last time that there was a lot of interest back in the 1970s in the role of incomplete information in explaining macroeconomic dynamics. And that earlier literature that Bob Lucas had kicked off with his famous business cycle model was, of course, based on the idea that decision makers didn't know everything that was going on, but it assumed that they made complete use and fully optimal use of everything that could be seen given where they were in the economy. And so incomplete information existed in the model that Lucas proposed because he proposed that decision makers were isolated from each other on what he called islands. And so the economy was made up of separate markets on a bunch of separate islands, and people knew everything perfectly that was happening on their island, but that didn't mean that they knew things like the aggregate money supply, which couldn't be observed from just observing what was going on your island. And a problem with developing that literature that developed fairly soon was that people began to ask whether it was really realistic to think that there was, for example, delays of any significant size in public awareness of, say, what had happened to monetary policy if it was based on the claim that it was not publicly observable, what the central bank had done with monetary policy, given that it's extensively reported on. The Fed, each time it makes a decision, they have a press conference immediately. There's a public statement released. It's extensively covered in the media for people who follow that sort of thing. And so saying that the information is not out there and is not observable to decision makers isn't obvious. This more recent literature has come back to suggesting that maybe it is desirable to assume that decisions are being based on less than complete information about what the current state of the economy is, by supposing that perhaps the bottleneck is not the physical organization of the world that's the relevant obstacle to full information, but perhaps that there are obstacles in the perceptual or cognitive capabilities of the decision makers themselves. And so they're paying limited attention to what's going on, even if in principle there's a lot of information that they could learn about if they were bothering to follow it. Now, of course, an obvious question about that that will occur to economists, and I think accounts for the fact that this has not been a natural move to make in economic theory in the past, is the objection that if you propose that what's in people's heads is not the same as what's in fact going on in the world, there's the fear that that means that now your theory has no content because you can assume anything you want if you're allowed to assume that what's going on in people's heads is something different than what reality is. So how can one respond to that? One could imagine different directions of trying to supply a more specific content to this assumption about what people are aware of, if it's not simply the truth about the environment they're in. One direction would be to say, well, this should be an empirical issue, and we should figure out what we know about cognition, and we should perhaps learn from cognitive psychologists or from the young literature in neuroeconomics. And I'm actually very interested in that direction, and I'll say some things about that too, but that's not the main point of this talk. I thought expected to talk about a literature that exists as opposed to a literature that should exist. So I'll talk mainly about the other bullet point here, which is to have a relatively parsimonious theory, and therefore one that makes fairly sharp predictions by introducing a strong theoretical hypothesis about what kind of partial information people might have, even if you're assuming that they don't simply know the true state, all the true state variables in the situation that they're in. What this idea, just in very general terms, is about is Chris Sims has proposed a hypothesis of what he calls rational inattention, which is to assume that people don't have perfect awareness of the situation they're in, but that to assume that specifically what they have more precise and what they have less precise awareness of is in fact an optimal choice given the decision problem they're trying to solve and given a constraint, an overall constraint on the complexity of the information that you're letting them have about their environment. And I'll have to talk about how that constraint is formulated. Why might we be interested in this class of theories? There are various types of things that models of this kind can offer explanations of. One that I'll talk about is the idea that this can provide an explanation for stochasticity of behavioral responses, for randomness of behavioral responses that don't simply follow from randomness of the fundamental determinants of the decision. Another thing that motivated Sims's early work on this, and a lot of the literature in this vein in the last decade, has been using the idea of models of inattention as an explanation for delayed adjustment to shocks of various kinds, that people don't adjust as fast as they would with full information exactly because of their lack of full awareness of the situation that they're in. Not just delays in general can come out of this kind of theory, but there's the promise that it could provide a reason for faster adjustment to some kinds of shocks than to others, insofar as one can make endogenous predictions about which things people should be more aware of and which things they should pay less attention to. Also, I wanted to point out that a theory that can explain delayed adjustment to shocks is not just a theory about why nothing should be variable. In fact, in many models, under-response of some variables is then going to require over-response of others. So a model that explains people changing their portfolios less quickly because they're not paying attention can easily be a model that will then predict that asset prices will over-respond to shocks. And so it can be an explanation of excess volatility of some variables by explaining sluggishness of other variables. Another general class of problems that one could be interested in is explaining what I call here stereotypy of responses, why there might be a limited repertoire of responses to different environments, even if the environments are much more variable. For example, there might be only a discrete set of responses, even though the environments, there's a continuum of different types of values of the environmental state variables. That may, in fact, follow from limited information that's optimal in the sense that Sims proposes. Finally, various kinds of cognitive biases that the behavioral literature has stressed, I think, might well be explained as resulting from an optimal kind of partial information of the kind that this theory is about. A lot of the literature has tried to propose bringing those things into choice theory by modifying people's preferences and assuming that they represent non-standard preferences of one kind or another. I think that perhaps one should think of them, though, as indicating something about perception of the environment as opposed to something about people's preferences. So I'm going to start by talking about the first of those problems because it's maybe the simplest to talk about as an illustration of what rational inattention theory is like. And this is explaining randomness of behavior that doesn't result from randomness of the underlying determinants of choices. And so, of course, what's problematic about that is that in the standard paradigm in economics is that we explain behavior as corresponding to maximization of some objective, maximization of utility or maximization of profits. And the general property of that kind of theory is it's going to imply that the choice should be a deterministic function of the characteristics of the alternatives that the decision maker is choosing between. In discrete choice problems, so ones where the set of alternatives are in fact discrete, you're going to do something or not doing it, the prediction of an optimization theory is that the choice should switch from one action to another if and only if the vector of characteristics of the choices that you have is on one side or another of a sharp boundary, the point at which the maximum of your utility function, the utility associated with one choice just becomes higher than the utility of the other choice. And so you should be observing this kind of sharp changes in behavior at certain thresholds. And furthermore, the outcome should be a deterministic function of the characteristics if you've properly measured them. In experiments, one observes that choice is observed to be random in the sense that, for example, a given subject doesn't always make the same choice when presented with the same alternatives. And certainly in experimental psychology, that's something that's been observed for more than a century, and it's a commonplace that one needs to model choice as being inherently stochastic, the sort of thing that would typically be studied in psychology is to try to study systematically how the probability of a given choice depends on the characteristics of the things that people are choosing between, rather than imagining that you're going to find a deterministic choice function. So that's what I meant by soft discrete choice that I had used as a heading, is this idea that the probability of choice is varying smoothly with characteristics of the situation that, say, maybe determine the true relative value of one option relative to the other one. Maximization theory would imply that the probability of choice should be a function like the one that the black dashed line is showing, jumps from 0 probability to probability of 100% at some sharp threshold, and instead what one often seems to observe is behavior more like that curve. Paul Glimcher, in his recent book, his manifesto for the development of neuroeconomics, as he sees it, stresses this is one of the big themes in the book, that he proposes as a leading respect in which he thinks a theory of choice with neuroeconomic foundations is going to have to differ from standard economic theory. This idea that you want to model choice as being soft in that sense is, of course, standard in the part of empirical microeconomics that studies discrete consumer choices, choices between different modes of transportation or different large consumer purchases or things of that sort. The type of models that are typically econometrically estimated are things like the Logit model, which is one very popular model in that literature, where you model the probability of choosing one of the options as a continuous logistic function of some vector of measurable characteristics. And you estimate the parameter vector of coefficients there that make this logistic function fit your data. Yes? Yeah.
It seems to me that you could explain this kind of behavior also with the traditional model.
Yes, I'm going to say that. That's what this slide starts with that. So what's the traditional explanation, the one that McFadden in particular developed, was to say, well, yes, it's random, but we're going to interpret as maximization of utility. We'll introduce the hypothesis of randomness in the utility function. So utility is a function of those characteristics that you're measuring, but there's some unobserved random term. And if the random term is of the right kind, you could explain that logistic function, which he and his collaborators often use in their empirical work, if the random term in the utility function is drawn from this extreme value distribution, then in fact you'll get that relationship between the probability of choosing one option and the other and the vector of characteristics. So why isn't that great? I mean, that's very famous. That's how the logistic model is taught. Before you teach people how to estimate it, you tell them this is the economist's interpretation of what it is that you're estimating. Well, I think this is a very strange distribution. First of all, why is your econometric program based on thinking that not just utility is random, but that you're going to hypothesize this very specific type of randomness? in the utility function. It's hard to think of a mechanistic interpretation of what the source of the randomness is that correspond to that exact kind of distribution. And so then that raises the question of whether the empirical work based on the logistic model, you shouldn't be worried about misspecification because the randomness might be of some very different sort than that kind. Another type of applied literature where this same issue of the softness of discrete choices has come up pervasively, and one that's of more relevance to macroeconomists, is there are lots of types of choices of firms changing their prices, changing their number of employees, changing their level of inventories, and so on, that are observed to adjust at discrete points in time. So instead of continuously varying these things, there are certain points in time when the price of a product changes, and then it's constant for a while. Certain points in time when the size of the workforce is changed discretely, and then it stays the same for a while. Certain points in time when a bunch of new supplies are ordered and the level of inventories jumps, which then moves continuously after that, and so on. And so there's a question of why do you observe these discrete changes if the environment that's determining the optimal price or the optimal number of employees are things that you think should be changing more continuously. Of course, again, there's a standard interpretation of that, of how that would be consistent with maximization, which is the hypothesis that there's some kind of fixed cost of adjusting whatever the variable is. And so the discrete adjustment is interpreted as reflecting the evident existence of these fixed costs. And so we're all familiar with optimizing models that assume the existence of those fixed costs. What they imply, of course, is that the adjustment should occur if and only if you cross some sharp threshold. That's the SS class of models. The terminology comes from Holt, Modigliani, Muth, and Simon's work back in 1958. They introduced this in the context of a model of inventory management, and it's been extensively used in lots of other areas. Empirically, that kind of model doesn't seem to work well. I mean, at least not as a function of characteristics of the situation that the people studying a given problem are able to measure and put into the model. Caballero and Engel, back in the early 1990s, proposed a generalization of the SS type of model, which in a series of papers they argued works empirically much better, what they called a generalized SS model, which in fact makes the choice soft rather than a sharp threshold. Their hypothesis is that there's in fact an adjustment probability. This probability of adjustment should be modeled as a continuous function of the measurable properties of the state, rather than there being a sharp threshold. This is an example of the kind of hazard function they estimate, taken from one of their papers back in the 1990s with John Haltewanger. So this is a model of employment adjustment by individual firms using firm-level data on the employees, number of employees each month, and other characteristics like the measured capital stock and wages and so on that they were using to calculate what they thought was the profit-maximizing level of employment. And in their model, there's a probability of adjusting your employees each month that's a continuous function of the gap here on the horizontal axis between your current level of employment and what they're calculating as your currently optimal level of employment. And so it's an increasing probability of adjustment on both sides of zero, on both sides of their estimating that you currently have an optimal level of employees. And so they hypothesize that this adjustment hazard it's not 0 or 100%, it's varying continuously with how far you are from the optimal level of employment. When they proposed that, it was a purely arbitrary thing. They were just saying we're going to fuzz up the theory and it'll fit the data better. And they had a whole series of papers that got a lot of attention that showed in various contexts that had some empirical value. There is a conventional interpretation of what that hazard function might mean that was developed a few years later. They had a paper in Econometrica in 1999 where they gave a theoretical interpretation to the hazard function as a random draw each period of the fixed cost. So it's a model where there's a fixed cost of adjustment. That's why you won't adjust all the time constantly. The fixed cost isn't a constant. You draw it independently from a distribution each time you consider whether to adjust or not. And it's the shape of that distribution of the fixed costs that you're drawing them from that's going to determine the nature of the hazard function. So then we can reconcile the randomness of the adjustment with maximization theory by the hypothesis that there's this unobserved random variation in the fixed cost of adjustment. There's a paper that people in the literature on pricing would all know by Dotsey, King, and Woolman that uses that as an interpretation of a hazard function for price adjustment. So why isn't that great? I mean, we all teach that interpretation, of course, of these models. So one thing that I think isn't great about saying, oh, it's a random fixed cost, that explains it, is that once you introduce this hypothesis, the fixed costs can be constantly being drawn again from some non-trivial distribution, is then you could have all kinds of results about the relationship between the adjustment probabilities and the true situation, because the distributions could be lots of things. So that's a relatively weak theory. It's not means it doesn't have any content, but it's relatively weak without some view about what, in fact, the distribution of fixed costs should be like. Furthermore, to explain the observed data in a lot of the applications in terms of a distribution of fixed costs, you need to assume a particular kind of distribution of fixed costs, which is logically possible, but kind of surprising. Namely, it's a distribution that has a substantial probability mass at the zero fixed cost. Why? Because of the large number of small adjustments that are often observed. So I showed you an example back here where the hazard function is bounded away from zero, even in the neighborhood of zero discrepancy between your state variable and its currently optimal value. That couldn't exist due to random draws of the fixed costs unless you have a substantial positive probability of drawing a zero fixed cost. Here's another piece of evidence that indicates the same thing. From discrete price changes. This is from Virgilio Midrigan's dissertation a few years ago that got a lot of attention, where he stresses the fact that in micro data sets, one observes the distribution of price changes even when price changes occur. So this is taking out the zeros and looking at the price changes on the particular points in time when the prices of goods are changing. He argues that these distributions are leptokurtic, meaning more mass in the center and out in the tails than is characteristic of a Gaussian distribution with the same mean and same standard deviation. And the puzzle there is that to explain that kind of distribution of price changes with a whole lot of quite small price changes relative to the standard deviation of the distribution, you need not just to draw the fixed costs from a random distribution, but you have to draw it from a distribution that puts a lot of weight on extremely low fixed costs. In fact, something like a big atom at zero.
And what were the two distributions that you were looking at?
These are two different micro data sets. The one is from the AC Nielsen that supplies the data to marketing departments. And this is the Dominick's supermarket chain in the Chicago area that supplied some of their data on their products, and that's been extensively used because of that. Finally, the theoretical interpretation involves drawing the fixed cost independently each time, each instant really, that you could make a decision about whether to adjust or not. Caballero and Engel are proposing that you make a completely independent draw from this distribution of fixed costs with a significant dispersion of what the fixed costs are, independent of what it was the last week or the last day or whatever was the last instant. when you thought about adjusting. And while you might say the fixed costs can vary over time, why not? That's plausible enough that there could be drift, random drift in the fixed costs. The idea that it's completely independent from one moment to the next is kind of a strange assumption. Logically possible, but I think kind of strange to believe that's literally what's going on, although it's what you would need for models like the two up at the top of the slide to be correct interpretations of the data. So the alternative interpretation that I want to suggest to you here is that maybe the randomness of the choice is in fact resulting from limited attention to the circumstance under which the choices are being made, not random variation in the actual costs of doing something or random variation in the actual payoffs that you're getting from doing something. Should you be interested in a strange thought like that? Well, it's not so strange, again, if you think about what the experimental evidence on perception has indicated for a long time, which is that in the branch of experimental psychology concerned with the relationship between subjective perceptions and the objective physical characteristics of the brightness of lights and the perceived heaviness of things that you're picking up and perceptions of tones and so on. That's the area called psychophysics. It's been observed for a long time, not just that subjects have limited ability to discriminate between non-identical but sufficiently similar stimuli, but specifically that their responses are random, and that what the literature studies is the relationship between the probability of judging that one sound is a higher pitch than the other one, say, and the true objective characteristics of the sound that you're supplying it. So one observes this apparent randomness of perceptions, of the relationship between subjective perceptions and the objective characteristics. If one thinks that that's a pervasive characteristic of human perceptions, then you would expect that, in fact, to have consequences for choice. It should, in fact, be a source of randomness in observed choices, and so that could be a possible interpretation of this soft, discrete choice that I'm describing. The conventional interpretation of the randomness of the responses in the psychophysics experiments for a long time has in fact been the idea that the perceived stimulus is some random function of what the true characteristics of the stimulus are. This book by Green and Sweats on what's called signal detection theory is a classic reference still in that literature, but the idea goes back at least to the work of Thurstone back in the 1930s. And what this kind of theory predicts is that there's a frequency of correctly discriminating between the two stimuli, saying which light is brighter than the other one. Fraction of the times the subject should get it right should be determined by the degree of overlap between the probability distributions of the subjective perceptions associated with each of the two stimuli. That's something that was originally just proposed as a possible theoretical interpretation of the randomness in the responses of experimental subjects. But now, something that the more recent neuroscience literature can contribute to this is we can actually verify this hypothesis of a random relationship between the objective characteristics of the stimulus and the way they're being perceived in the nervous system by actually measuring, in the case of animal subjects at least, this relationship. So a famous example of that is this study by Britton and co-authors, where what they're observing is the ability of rhesus monkeys to discriminate correctly the direction of motion of moving dots. So the monkeys look at dots on a screen. The dots are not all moving the same way, but a bunch of the dots exhibit coherent motion in the same speed, in the same direction. There are other dots moving in other randomly drawn ways. And the question is, can the monkey correctly answer whether the dots are mostly moving to the left or to the right? They get juice when they get it right. And so they learn. They learn to do this because they like getting the juice. And you can also measure then what's going on in their brain while they do it. So here is what some data look like. This is the histograms for the number of times a particular neuron in the middle temporal region of the monkey's brain, which is the region of the brain that's known to be involved in perception of direction of motion. Number of times the neuron spikes while the monkey is observing the stimulus and making the decision, as a function of the objective characteristics. The objective characteristics are these percentages over here are the percentage of the dots with the coherent motion, and the white histograms are when the coherent motion is to the right, the black histograms are when the coherent motion is to the left. So what you observe is that there's a probability distribution of number of times that the neuron spikes rather than it being a deterministic function of the characteristic of the stimulus. In the case that the motion is more coherent, the degree of overlap between those two probability distributions is becoming less and less, and so the prediction is that it should in fact be, the monkey should in fact be able to be more successful at telling apart the leftward motion and the rightward motion to the extent that the probability distributions are not overlapping as much. What this figure shows is two things. One is a plot, the so-called psychometric function is the classic thing that people in this literature do, also with human subjects. The black dots are showing the probability of getting it right as a function of the degree of coherence of the movement of the dots. And so the probability is only around 0.5 when there's little coherence. It rises to almost 100% of the time right if there's sufficient coherence in the motion. But again, instead of there being a threshold required for getting it right, it's this somewhat, to the extent that the data are telling you, it's looking like, consistent with this hypothesis of the smoothly increasing function. That's what the black dots are showing you. The white dots are asking, given those measurements of the probability distributions of number of spikes in the neuron, what would your prediction be about how often the monkey should be able to get it right if the monkey is optimally making use of the information in the mental representation as revealed by the number of spikes in the neurons? That's what the white dots show you. And the answer is the randomness in the measured activity in the neuron is doing a pretty good job of explaining the nature of the randomness in the monkey's actual response. Okay, so what do I make of that? What I think this means is that we want a theory. First of all, of course, it's a theory where it's a case where perceptions are just not a simple, correct representation of the stimulus. But furthermore, I think it's support for the view that we want a theory where the mental representation is, in fact, a random function of the true characteristics of the stimulus. That's certainly what we're measuring here in the case of the monkeys. So if you take that seriously, it means you're not going to model partial information in the way that, say, Elanon was in his talk yesterday, where he assumed that there's a true state of the world. People don't know the true state of the world. What do they know? They know which element of a certain partition the true state of the world belongs in. And so that's a classic way that game theorists like to model partial information. It's the way you would naturally model it if you think the brain is a logic machine, and so whatever it does, it must be some Boolean function of some kind or another. So it's implying that the signal people get is a deterministic function of the true state. I'm going to consider theories in which that's not going to be true, and I think this experimental evidence pushes one in that direction. Another comment is whether the type of partial information assumption common in the global games literature is consistent with this kind of evidence on how the brain works. And, well, partly because the assumption that there's private information which could be the true characteristics plus idiosyncratic noise of some kind gets an explanation here. This would be an explanation of where the idiosyncratic noise comes from. It can be in the brain of the observer. On the other hand, it's a big topic of discussion in that literature where you assume that there can be private signals like that, and then there can also be public signals that it's assumed all the players in the game will observe in exactly the same way. If you take this view of the nature of partial information seriously, it's going to imply there can never be any such thing as the public signals. Right? Because something that's happening out in front of everyone and you're all looking at me and you think you must all be seeing the same thing, this theory says, no, each of you are seeing something that's randomly related to what's really up on the stage, and so it's in fact all private signals. Anyway, if you believe that. Okay, so I should probably move on. To telling you something about what the structure of a model is like that's going to not only just introduce this idea of the random relationship between the subjective representation and the true state, but endogenously model the nature of that relationship. So suppose we have a problem where there are two actions which are, say, to adjust or not adjust the size of your labor force or your price, something of that kind. There's going to be a payoff from adjustment or a loss from non-adjustment, which will be a function of some state variables. This x is a vector of variables that can vary continuously. They're going to describe the relevant features of the state of the world that determine the relative payoffs from doing the two things. I'm going to assume it's a continuous function. There's going to be a prior, because if we're going to talk about optimality of the perceptual processing, it's going to have to be optimal relative to some prior over what the frequency distribution of in fact being in different situations is. And so this f of x is the prior with respect to which we're going to hypothesize that the perception might be optimal. The model of cognition is going to be there's going to be some subjective representation R, and conditional probabilities of the different subjective representations are conditional on what the true vector of characteristics are. So I'm letting R be a random function of x, although we're going to derive endogenously what kind of function it should be, and indeed whether it should be random or not. It's not that I'm going to exclude the possibility of a deterministic relationship. That'll be one of the things that this set of conditional probabilities could be representing. The action will then have to be chosen as some function, maybe a random function, of the subjective representation R. So the limits then on attention, it's going to depend what kind of conditional probabilities of R conditional on X are going to be possible for people. And Sims's proposal is that you should constrain the set of relationships between R and X by some limit on the rate of information transmission in binary digits per transmission over the communication channel that's being used to go from what's really out in the world to getting it into the mind of the decision maker. This is going to be a quantity that can be calculated from the joint distribution of X and R. So the assumption about those conditional probabilities in the prior will imply some joint distribution of X and R. Given that, we can use information theory to calculate what this rate of information transmission is, and Sims is going to say, well, it can't be bigger than a certain number. That's what's going to limit the possible conditional distributions. Alternatively, we could suppose there's some cost of having a higher rate of information flow and introduce a cost parameter theta, and we could ask for the information processing to be optimal, subject to some cost of requiring more complex knowledge represented by a higher value of this rate of information flow. So what's the rate of information flow going to be? In the case that you observe a subjective representation R of your situation, we can compare your posterior, if you calculated a correct posterior conditional on observing R relative to the prior over X, that was the f of X. The posterior is calculated, of course, with Bayes' law. The pi's are those things that were p's on a previous slide. Sorry about that. Those are the conditional probabilities describing the nature of the randomness of perception. And so if we're using entropy as our measure of uncertainty about what the state of the world is, this is telling you how much uncertainty is reduced by observing the subjective representation R, at least if you made optimal use of the information. So we can furthermore calculate an average value of that over all the possible subjective representations and the frequencies with which they'll occur according to the prior, and that gives us an overall rate of information flow I. This is the measure of mutual information as defined by Claude Shannon, and we'll be assuming there's either an upper bound on that or that there's a cost to the decision maker that is an increasing function of how much information you're using. So now we can state our formal problem. We want to choose a stochastic relationship between the subjective representations and the true state of the world. And we're going to choose a function which gives you the probability of action as a function of the subjective representation so as to maximize this objective function. In this objective function, the I is the thing defined on the previous slide. That expectation operator means you integrate the value of lambda times L over the joint distribution of R and X. The joint distribution of R and X is defined by the prior and those conditional probabilities. Okay, so that's a well-defined object. We want to maximize that. A first result about the nature of the optimal representation to solve this problem is an optimal representation at least can be assumed without loss of generality for this discrete decision problem to simply be a signal whether to act or not. So we only need a binary signal because more information than the signal whether to act or not is going to be redundant information about the current state. It'll increase the size of I, that cost of information, and not improve, not lower the value of expected losses, or sorry, not increase the value of the expected gains in that first term, and so it won't be efficient. So then I can reduce the design problem to the choice of a hazard function. I can just assume that the signals are yes and no, act or don't act, and the hazard function will say the conditional probability of getting the signal to act as a function of the vector of characteristics. So now we're into the kind of framework that Caballero and Engel hypothesized. We've got this hazard function. It's going to come out as a property of the optimal perception that it should be able to be described in terms of some hazard function. But we can furthermore derive what the hazard function should be like by solving the optimization problem. So first I can rewrite the optimization problem now in terms of the hazard function. So now my objective and my constraint are entirely written in terms of the loss function L of x, the prior f of x, and the hazard function now, lambda of x, and that's equivalent to what I defined before. And so we can maximize now. That's a calculation of variations problem. The solution could be of three types. It could be optimal never to act. It could be optimal always to act. And in any case, except those extreme ones, the solution looks like this. The optimal hazard function is going to be a function of x of that form, where lambda bar is going to be a quantity between 0 and 1, which is in fact the average frequency with which you act. So it's going to be the integral of lambda of x under the prior. So that up to that one parameter, knowing the theta, the cost of additional use of information, that's pinned down exactly what the optimal hazard function should look like. And you can figure out what the lambda bar has to be for it to be consistent with the lambda of x. And so you can in fact show that there's a unique solution. And except when you're at those two extreme cases, that you either always act or you never act, then it's never going to be the case that you sometimes don't act with certainty and sometimes do act with certainty. There's no sharp threshold. Instead, lambda of x is always going to be strictly between 0 and 1, and it's going to be an increasing function of L of x. If L of x is a continuous function, it's going to be a continuous hazard function. If L of x is a smooth function, it's going to be a smooth hazard function, and so on. What kind of general things do we learn from that? Well, this is a theory that in fact says choice should be not just possibly stochastic as a function of those objective characteristics x, but necessarily stochastic. Unless you're in one of those two extreme corner solutions, choice will always be stochastic. The probability of acting will always be strictly between 0 and 1. So unlike some of the examples that Caballero and Engel hypothesized, when they just hypothesize different hazard functions, it's not going to be optimal for there to be some zone of inaction over which there's no probability of acting, nor is there going to be, in this model, any case in which you would have an incentive extreme enough to make it completely certain that the adjustment has to occur. So Glimcher's claim that we need to get stochasticity of choice into choice theory would be gotten in this way. He suggests that maybe the reason, he suggests a possible functional explanation for the randomness that he says is in the brain, which is that maybe it has evolutionary advantages because it makes people keep experimenting, which might be good, and that might be true, that that's good. I'm proposing a functional explanation that's completely independent of anything like that, though, which is that if this is the nature of the constraint, in fact, an efficient perceptual system in the sense I've defined will, in fact, be necessarily random. Another interesting thing about it is that it can provide an explanation for the logistic model turning out to be empirically useful in discrete choice situations. It, of course, doesn't have to be, but the case in which the logistic model would be the prediction of about the optimal hazard function is a simple case, and so a fairly natural one, namely the one where the utility function is linear in those measured characteristics. So there's no randomness in utility. This is no assumption about the probability distribution for the random term, because there is no random term in the fundamentals. Getting it to be exactly logistic does depend on it being exactly linear up there, but of course that could be an approximation. If the utility function is sufficiently smooth, then there's some small enough range of variation in the characteristics where we should expect approximate linearity to be correct, and so approximately the logistics should be working over some range. You would in fact expect that to be a fairly pervasive finding. So that's I think a nice thing about this. There's a recent paper by Philippe Mateka and Alasdair McKay that discusses this interpretation of logistic discrete choice models in terms of rational inattention, that discusses this in detail. Finally, the generalized SS model proposed by Caballero and Engel can easily come out of this, again, except in those extreme corner solutions. If the loss function is itself continuous, you should get a continuous hazard function varying continuously between 0 and 1. To the extent that you like the random fixed cost models, in fact, this is not contrary to them. This is a theory that predicts that it's equivalent to a particular distribution from which the random fixed costs are being drawn. So instead of being a very flexible theory, it makes a much sharper prediction. It corresponds to a particular distribution of random fixed costs. I think it has some advantages over the random fixed cost interpretation. With the random fixed cost interpretation, it might seem very odd to think there should be a big atom at the 0 fixed cost. This instead predicts that necessarily the hazard function remains bounded away from 0 everywhere on the state space. So that's not a weird case, that's the necessary case. The independence of the noise each time you consider whether to adjust or not comes naturally out of this prediction about the nature of the optimal imperfection in perceptions, rather than being an extremely special and, I think, implausible case that you might be assuming about the distribution of random fixed costs. How much time do I still have? So I will have to be very quick. I should say something, though, about the idea of using these models to explain adjustment delays, because I think that's been one of the big interests of the literature. Once you understand that the model is going to predict a random relationship between the true characteristics and subjective perceptions, then, of course, decisions, the optimal decision using that information will depend on your best estimate of the true.
25.
Okay. Okay. So your best estimate of the true state conditional on the subjective perception. That was the hypothesis about the monkeys, if you'll remember. You measured the random state in their brain, and then you asked what would their optimal action be if they were making the best possible use of the random state of their brain. So if you're doing things that way, knowing, or at least your criterion for optimality takes account of the randomness in the representation, it's going to mean your optimal estimate is going, on average, will vary less than the variation in the true state, so it'll naturally give you underreaction to changes in the true state. It'll also give you partial adjustment behavior, not just in the sense that the immediate response to a change in conditions is less than the response that would occur with full information, but that over time you'll get more of the adjustment occurring. Why can it not what?
You said underreaction, you said.
Yes.
Why under? It could be either over or under.
No, because you're going to form an optimal estimate of what the true state is conditional on the thing that you're observing. Okay. And so if the thing that you're observing isn't giving you such good information about what the true state is, then your optimal estimate will not vary too much when you get your random observation.
But it's not, it won't be under. It could be symmetric or random. No?
Oh yeah, no. This is saying, is the derivative of your action with respect to the change in conditions larger or smaller than the derivative if you had full information. And the claim is you'll naturally get less response in that sense of the smaller absolute value of the derivative coming out of the noisiness of the perception. But you can also very directly get, with repeated noisy observations of an environment where there's correlation over time in what the state is, you can get the fact that when a shock occurs and changes conditions, the immediate adjustment will only be partial. Then over time, that shock will be predicting further adjustment occurring later, as in partial adjustment models, but without just assuming an ad hoc partial adjustment function or without assuming convex adjustment costs as a way of getting partial adjustment. There are no true adjustment costs here at all. Now, apart from being able to get behavior like that without the assumption that there are any true adjustment costs, I think something that's particularly interesting about the rational inattention type of interpretation is that it offers the possibility of explaining why some events might affect behavior and be incorporated into behavior much more rapidly than other types of events. So two events that have an equal size impact on what your gains from adjusting are, or that change to the same amount, the size of your optimal adjustment if you were fully informed, the model can give you a reason why you might more quickly respond or more fully respond to one of those events than to the other. Why? Because you might have a reason to be paying more attention to one type of event than the other. What would be a case where we're interested in having a theory like that? It's the observation that firms seem to change their prices more rapidly in response to firm-specific cost news, say change in the prices being charged by the firm's suppliers, than they do to changes in aggregate demand conditions like the Fed tightens monetary policy. And so a question, it's difficult for a theory of sticky prices or some kinds of sticky information models like the Mann-Q-Rees model, where people simply, for exogenous reasons, update all of their information and get perfect information, but only at discrete points in time. Neither of those types of theories give you a reason why you should more quickly incorporate some kinds of shocks into your behavior than others, whereas the rational inattention type theory, at least potentially, offers the possibility that you might be able to explain this by having a theory of why it might be optimal for people to be allocating more of their attention, say, to the price of their suppliers than they're paying to what the recent monetary policy decisions have been. So to illustrate how that could come out of a model of optimal attention allocation, I want to talk about a simplified version of a paper by Bart Moskaliak and Mirko Wiederholt in the AER back in 2009. They have a complete dynamic stochastic general equilibrium model. I'm going to do a sort of a baby version of it to explain to you where their result is coming from. Suppose that each of our firms is going to choose a log of its price, PIT. It's going to choose this price each period. But it wants to choose a price that minimizes its losses from having the wrong price, and we'll suppose its objective function is a quadratic loss each period in the discrepancy between its price and these two state variables, x1t and x2t, that are evolving independently of its own decisions. x1t and x2t are random things happening out there, both of which affect the firm's optimal cost, or optimal price, rather. x1t is common to all the firms I. x2 with the I superscript is some idiosyncratic random event that relates only to firm I, and so each of the firm I's, that'll be an x2 variable, but they're independent across the firms. And I'm going to assume here that also these two random states are evolving independently of each other. Specifically, to make the calculation simple, I'm going to assume each of them is an independent random walk. The innovations in the random walks are drawn from a normal distribution with a mean of 0, but the variance of the two random walk innovations can be different for the two components, and that's what's going to possibly result in it being optimal to pay more attention to one of them than another. I'm also going to simplify the pricing problem of the firm by assuming there's no strategic complementarity, so the firm only needs to track what's happening to these variables that are assumed to be evolving independently of the pricing policies of people in the economy. Okay, well, so the optimal price, conditional on your private information, is obviously the sum of your private estimate of x1 and your private estimate of x2, taking the correct conditional expectation, conditional now on your random subjective perception of the current state of the economy. We have to figure out what that random subjective perception is going to be. I'm going to suppose, furthermore, in my analysis of the attention allocation problem, that the firm has to separately observe the two components. So it'll have a subjective representation R1 of the current value of x1. It'll have some subjective representation R2 of the current value of x2. What do I mean when I say it's a representation of the current value of x1? I mean the distribution of values of R1 can only be a function of the true value of x1. It won't be a function of x2. Similarly, the probability distribution for R2 will be a function of x2, but not allowed to be a function of x1. The constraint is going to be an upper bound on the total rate of information flow, which is the sum of the information flow in the representation of the x1 and the information flow in the representation of x2, which are these two independent information processing channels. And the I1 and I2 are defined as on the previous slide, depends on the joint distribution of the R and the X. It turns out what Moskaliak and Wiederholt show is that for this kind of problem, the optimal information structure, and this is also assuming that we start off with priors about the x1 and x2 that are independent Gaussian priors, then you can show that the optimal information structure is going to be able to be represented as saying that the subjective representation of R1 or R2, whichever one it is, of Rj is the true value xj plus a normally distributed measurement error, which is independent of the other observers, independent over time, independent across these two communication channels. So that's like the global games assumption, except it's arising endogenously as what an optimal subjective perception would be, subject to this information theoretic constraint. Given that that's your subjective representation, the optimal estimate of the current state will then be a multiple of that random signal, Rj. The multiple is this factor, which is strictly between 0 and 1. It's going to depend on the variance of your prior for the state xj in the particular period t before you observe that period's signal. And that itself might be evolving over time. And the nu squared j is the variance of the noise in up there. That's the variance of the measurement error term for your observation of j. And that also may still be time varying. We haven't yet pinned down what it is. But now I can reduce the problem by saying if we know that the optimal perception has that form, then we know the mean squared error, the estimate, will be that function of the beta and the prior uncertainty, the capital sigma, and the beta in turn followed from the capital sigma and the nu squared term. We have a law of motion for the priors. This is just follows from Kalman filtering or Bayesian updating. Again, making optimal use of the signals, and we can define the joint. We can solve for the joint distribution of the R and the X's and measure this rate of information flow in each of the two communication channels. It'll be this function of the sigmas and the nus, and so now I can rewrite my decision problem as a choice of the amount of information processing capacity to allocate each period to each of the two channels and solve for everything as a function of the I1 and I2 each period. And I get a problem that can be written in recursive form in this way. We can define a value function at each point in time, which is just a function of the two prior variances, the capital sigma 1 and the capital sigma 2. And that value function solves a Bellman equation like this. The first term there is the sum of the two contributions to the mean squared error of your decision, which is just the sum of the mean squared error in your estimates of the two underlying state variables that I've solved for on the previous slide as a function of the prior uncertainty and as a function of the rate of information flow, Ij. The second line is the upper bound on the sum of the two rates of information flow. And the third thing is the constraint on how the prior uncertainty will evolve, how it will evolve as a function of your decision to allocate more or less attention to the observation of that particular state variable each period. Okay, so then we can solve that problem in a straightforward way. And what you find is that the optimal allocation of the I1 and the I2 in the steady state is going to be constant. That IJT will in fact be a constant because the solution to this equation will be independent of time. And it's going to solve the same equation for both values of j, except it'll depend on the variance of the innovation in the random walk of the state variable x1 or x2. And since that function phi of I on the left-hand side is an increasing function of the rate of information flow, this is going to imply this, which is that the relative size of the two rates of information flow, I2 will be bigger than I1, which will imply that the beta 2 will be bigger than beta 1 if and only if the variance of the innovations in the x2 is bigger than the variance of the innovations in the x1 random walk. So whether or not you have faster adjustment, this is going to tell you how fast the partial adjustment is to changes in x2 versus the rate of partial adjustment to changes in x1. You'll adjust faster to changes in x2 if and only if you allocate more information flow to being aware of state x2 than you allocate to being aware of state x1, which it will be efficient for you to do if and only if the innovation variance in that component is bigger. So, for example, you could explain the faster response of prices to cost changes in idiosyncratic cost conditions if you think the variance of that idiosyncratic random walk is bigger than the variance in the changes in aggregate conditions. That's what Moskaliak and Wiederholt argue for in the calibration of their model. The basic evidence that suggests that that innovation variance should be a lot larger is that we observe that relative price changes, looking at different goods in the economy, are very large relative to the amount of variation in the overall rate of inflation, at least they were calibrating their model to the US in recent decades. One observes that. That implies one needs to have the relative variances be like that. Okay, so the model is successful in explaining what they wanted it to explain, at least from the point of view of that question of whether the relative variances make sense that they need to explain their result. Another question I should mention, though, because this relates to how we think, what kind of theory we think rational inattention is this result does depend not just on a finite bound on the total information flow, but on another constraint that I didn't really point to as it went by, which is that in their work, there is this constraint that you have to be separately observing x1 and x2. There have to be these two completely independent communication channels. So you can't have signal. You can have signals of an arbitrary kind that are functions of x1, signals of an arbitrary kind that are functions of x2, but you can't have a single signal that's a function of both variables. Is that innocuous? No. If you follow the pure version of rational inattention as proposed by Sims, which is just to have an upper bound on overall information flow and no constraints at all on what the subjective representations could be like, then in fact you would say you want to have a vector R of observations that can be some random function of the vector x and constrain it only by an overall bound on the mutual information between those two vectors, which is perfectly well defined. And what you would conclude if you did that exercise is, well, this is a model where the decision maker only cares about a certain linear combination of the two state variables, so it will only care about having a random signal that's some function of that linear combination. You can easily show that the optimal information structure will be to observe a single signal that I'm calling here pi star, which will be a noisy observation of that, the R will be a noisy observation of the pi star, which is that linear combination. The optimal action will be some multiple of the signal, which means the optimal action will be a linear function of that sum of x1 plus x2 through some coefficient beta, which will be less than, between 0 and 1. And so you're going to get the same rate of partial adjustment to all shifts in p star, the optimal price, regardless of whether it's the x1 or the x2 that's changing. So in fact, the thing they were interested in would not come out if we used Sims's more parsimonious version of the rational intention theory. What should we conclude about that? I mean, so you might conclude, okay, so rational intention, if taken really seriously, didn't explain the thing they wanted it to explain. My view is actually, I think their explanation is an appealing explanation. I think it means that the right direction to go with the theory is that we're going to need additional constraints on the possible structure of information processing rather than thinking that, as Sims proposed, there could just be a single global limit on the rate of information flow. And that brings me to the question of how the theory should develop, whether it should be a theory that we think we can develop just axiomatically on the basis of how beautiful the assumption is about what the constraint is, or whether there should be more of a dialogue between empirical evidence and what you assume the constraints on the structure of perception are. This is an example of where I think there should be more of a back and forth between the theoretical development and what seems to explain the evidence. This is still a pretty indirect kind of evidence, of course. Maybe the evidence that Moskaliak and Biederholt are trying to explain, you might think, doesn't relate to randomness of perception or anything. I mean, maybe you think it should have some other completely different kind of explanation. And I think the way we need to go, since I'm about out of time, I'm going to skip over further applications and jump to the question of whether we can't find more direct experimental evidence on the nature of imperfections in perception by looking at the literature on studies of sensory perception and asking whether, for example, the Sims formulation of the nature of the allocation of attention is matching the experimental evidence or not. So I want to give you an example of a study that I think is particularly interesting because it's studying pretty much exactly the thing that Sims's theory is about, except not in an economic context, which is it's asking whether the allocation of attention depends on the characteristics of the environment in systematic ways and whether it can indeed be viewed as an optimal response to changes in the characteristics of the environment. So this is a paper in the Journal of Experimental Psychology. And the experiment is subjects, these are human subjects now, the subjects look at a screen and a letter, E, T, or V, is going to briefly appear on the screen and they have to say which letter it was. And it only appears for 25 milliseconds, so they have, they're not entirely accurate at getting the letter right, but it's there long enough that their responses are not completely random either. The letters can appear at different locations. So there's a circle. There are different 8 locations equally spaced around the circle. They're supposed to be looking at the center of the circle. The letter will appear at one of the 8 locations on the circle. The 3 letters occur with equal frequency. The 3 letters are chosen so that it should be about equally difficult to discriminate one from another. You can measure that, of course, experimentally. And there are 2 different experimental setups. In the first one, and people are trained in this environment to learn how to do it, there's a uniform probability of appearance of the letter at each of the 8 locations. In the second experimental design, and the subjects are trained for a while to get used to how to deal with this environment, it's an environment in which the probabilities of appearance of the letters at the different locations are not uniform. In some locations the letter is more likely to appear, other locations it's less likely to appear. So the question is, does the accuracy of the identification of the letter across the different locations where the letter might have appeared depend on what the probability is of the appearance of the letter at the different locations? So if it is different, if the accuracy is different at different locations, that it tells you how people are allocating their attention. The true probability of appearance of the different locations might arguably affect what the efficient allocation would be. So this is what the experimental data look like. This is experiment 1 is the case where the frequency of occurrence shown by the gray bars is uniform at the 8 locations. And the triangles, which are the experimental data, are showing for subject 1 a very constant probability of getting it right about 2/3 of the time. So purely random answers would be 1/3 of the time. They're doing better than that, but it's a lot less than 100%. But their ability to discriminate between the 3 letters, while imperfect but partial, is quite uniform across the 8 locations. The interesting thing is now in experiment 2, the frequency of occurrence will not be uniform. They'll occur more often at 0 degrees and 180 degrees, least frequently at 90 degrees and 270 degrees. The bars show the frequency of occurrence of the letters at the different locations. The blue triangles are now, again, the experimental data on how often the subject gets it right when the letter appears at that location. Now the probabilities are no longer uniform of getting it right. And what you see is that they get it right more often when the letter appears at the location where it in fact appears more often, consistent with the view that they're able to become more precisely aware of things happening at that particular those locations in the visual field at the cost of having a decline in their ability to get things right at other locations. And so that's in fact indicative of some ability to allocate one's degree of awareness of different things that are happening in the environment, and arguably the allocation is shifting in a way that is efficient for solving the problem that you're confronted with, given the prior, a correct understanding, optimized with respect to a particular prior, over what the true states actually are. Okay, so that's the thing that Sims's theory is about. And so the question is, does the theory in fact rationalize the results? So the first thing to observe about the pure theory of rational inattention, where there should just be an overall constraint on information flow, no constraint on how the subjective representations might be a function of the state of the world, you observe that only the letter is payoff relevant, so an efficient signal will only be a function of what the letter is and be no function of the location. Since the frequency of the letters occurring is the same in experiments 1 and 2, then the optimal channel will be the same in experiments 1 and 2, and the probability of getting it right will be the same at all locations in both experiments 1 and 2. So that kind of theory will fail to explain the allocation of attention in the experiment. Well, so a hypothesis that I think is attractive, at least to me, is to say, well, evidently you can't choose to be aware of the letter without being aware of the location, no matter how desirable to you it might be to be able to structure your awareness that way. Evidently, you have to have parallel processing of what's going on at these different locations, and you need an additional constraint of that kind. So suppose we introduce the additional constraint, which is that the subjective signal necessarily reveals the location of the letter, but it can be a random function of what letter it is. And so we'll introduce that by supposing that the subjective representations there's a set of possible subjective representations for each of the locations I. They're mutually disjoint, which means that when you get a particular subjective representation, it tells you with certainty which location something occurred at, but it might be randomly related to what the letter is at that location. Okay, suppose we add that additional restriction, but the constraint is still Sims's constraint, which is there's an upper bound on the mutual information, the total mutual information as measured information theoretically. We can calculate that. There's mutual information now as a function. I've transformed it into being a function of the error probabilities at each of the locations. We can maximize it. Since I'm running out of time, I'm skipping through this. But you can show that it reduces to choosing the error probability at each location to minimize an objective like this, where this theta is a Lagrange multiplier on the overall rate of information flow that you're using. And the solution to this problem is that the error probability at each location should be a quantity E star that minimizes this function that I haven't really had time to explain to you where that function comes from. But in fact, if we apply this criterion as the constraint on possible subjective representations, we again get the conclusion that the error frequency should be the same at all locations regardless of what the probabilities are of the appearance of the letters at the different locations. So again, we cannot explain what is observed in the experiment with that theory. What do I think is wrong with it? Well, the mutual information criterion is penalizing highly informative signals only in proportion to the frequency with which they're received. So it's in fact not costly to be able to tell ET and V apart at the low frequency location just as well as you can at the high frequency location, because the cost to you in the information criterion of getting the good signal about the low frequency location is a cost that's only proportional to how often you have to get the signals, which is proportional to how often the letters are actually at that location. What I think we need then is a theory in which there's a penalty assigned to the capacity to receive highly differentiated signals, regardless of the degree to which that capacity is being utilized in the environment that you're in. That leads to an alternative hypothesis where the upper bound is not on the mutual information, but on the maximized value of the mutual information over all possible environments. And if I assume an upper bound on that and do the optimization problem, I'll just tell you I can do the optimization problem. Now the green circles are the prediction of the theory. And there are no free parameters in the theory. Once I've assumed the nature of the thing that there's the upper bound on, I can calibrate the overall rate of information flow, or that capacity constraint, from assuming that it's the constraint in the uniform experiment. So I can parameterize my upper bound from the behavior, how accurately the subjects get it right in the uniform experiment. Now I've identified all the parameters of the model, and I have a model with no more free parameters to adjust to get the data right. And the green circles tell me what the theory predicts about the frequency with which you should get it right at each of the locations. And it's certainly predicting a shift in the allocation of attention. That's qualitatively what they found. Even quantitatively, it's not doing too badly for a model with no free parameters. So that leads to an alternative direction of development of the theory, trying to come into more contact with the evidence on the nature of perceptions. What's it telling us about how rational inattention theory needs to develop? In my view, first of all, it needs additional constraints, like the necessity of independent processing of information from different sources, which is not part of the classic version of the theory. Secondly, I've suggested an alternative cost function, a bound on processing capacity rather than on the rate of information transmission, might be the right constraint. Does that matter for economic applications? I've showed you that could help me in explaining these experiments in the psychology literature. Well, yes, because independent processing constraint was what Moskaliak and Wiederholt needed to explain the differential sensitivity to different types of shocks. It's also what I need in a recent paper of mine to explain some behavioral biases in the behavioral literature. What about the idea that it's capacity cost rather than a bound on information flow? That's what I need in my recent paper to explain apparent risk aversion over gains and risk seeking over losses in the Kahneman and Tversky type experiments, which are things that I analyze as reflecting not preferences but distortions in perception. I only get those kind of distortions in the perception with this bound on processing capacity. They would not follow with the Sims type bound on the rate of information flow. I guess I don't have time to say more than that.